Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're moving from the theoretical foundations of embodied intelligence to concrete examples of how it's put into practice. Our journey today takes us through Part 3 of Understanding Intelligence by Rolf Pfeifer and Scheier, specifically focusing on chapters 6 and 7. Last time, we discussed the limitations of classical artificial intelligence, or AI, and the crucial role that a physical body and direct interaction with the real world play in intelligence. This leads us to our central question for today. How can surprisingly simple, direct interactions between an agent's body and its environment lead to complex, intelligent-looking behavior without relying on intricate internal thinking or pre-programmed plans? Part 3 of the book, Approaches and Agent Examples, is all about illustrating these ideas with fascinating case studies. We begin our exploration with Chapter 6, which introduces us to the ingenious creations of neuroscientist Valentino Braitenberg vehicles. These aren't necessarily physical robots, but rather thought experiments, conceptual agents designed to demonstrate how remarkably sophisticated behaviors can emerge from extremely simple internal mechanisms and direct connections between their sensors and motors. The core idea here is what Braitenberg called the law of uphill analysis and downhill invention. It's often surprisingly easy to build a system that works, but incredibly difficult to analyze and fully understand why it behaves the way it does. These vehicles beautifully illustrate the frame of reference problem we've discussed. What an external observer sees as complex behavior might be the result of very simple local rules. Let's look at a few examples. Imagine Vehicle 1 with just one sensor and one motor. The more stimulation it receives, say, from a light source, the faster it moves. Even this basic setup, when introduced to environmental factors like friction, can exhibit complex, curving paths, appearing to like or dislike certain areas. Then there's Vehicle 2 with two sensors and two motors. Depending on how these are wired, it can appear cowardly, turning away from a stimulus, or aggressive, moving directly towards it. A particularly striking example is when a group of these simple, light-seeking robots appear to help each other. If two robots get stuck, their combined lights create a brighter spot, attracting a third robot that then bumps them free. There's no intention to help programmed in. It's simply an emergent behavior from their basic light-seeking rule. This powerfully demonstrates how complex social interactions can arise from local, simple rules. Braitenberg also introduced inhibition, where more stimulation leads to less motor power. This allows vehicles to approach a stimulus and then slow down or stop as they get very close, appearing to value or be attracted to a specific intensity. The timid vehicle is a great example. A simple avoidance mechanism combined with a constant forward bias allows it to navigate complex mazes without hitting walls. This shows how coherent, sequential-looking behavior can emerge from parallel, simple processes interacting with the environment, rather than from a pre-planned sequence. Moving on to Chapter 7, we encounter the subsumption architecture, developed by Rodney Brooks at the MIT Artificial Intelligence Laboratory. This approach has a more engineering-focused flavor, aiming to build robust, multi-goal robots that can be incrementally extended. Brooks's architecture is a radical departure from traditional AI, which often followed a sense model plan act (SMPA) cycle, where a robot first senses, then builds an internal model of the world, plans its actions, and finally acts. Subsumption, in contrast, proposes decomposing a robot's control into a set of task-achieving behaviors or competences, organized into layers. Here's how it works. You start with a basic level of competence, like avoid obstacles, level 0. This is implemented as a layer of control. Once this layer is built and working, it's theoretically never changed. You then add higher levels incrementally, like wander around, level 1, or collect objects, level 2. The magic lies in subsumption. Higher layers can suppress the inputs or inhibit the outputs of lower layers. For example, a collect layer might inhibit the avoid obstacle layer if the robot needs to push a chair to collect something. This design emphasizes direct sensor-actuator couplings with minimal internal processing, leading to robust, real-time behavior. Each layer functions relatively independently and intelligence emerges from the interaction of these loosely coupled parallel processes. These layers are built from augmented finite state machines, or AFSMs, simple computational devices that change state based on input and current state, with added features like timing mechanisms. The book illustrates this with compelling examples. A myrmex is a robot designed to find, eat, and digest objects. Its layers for safe forward motion, obstacle avoidance, and collecting objects show how suppression and inhibition links allow higher-level goals to override lower-level reflexes when needed. A Genghis, a six-legged walking robot, demonstrates how complex locomotion can emerge from distributed control. Its walking gait is built incrementally, layer by layer, with no central planner coordinating all six legs. The ambitious Cog project, a humanoid robot, pushes these principles to human-level intelligence, exploring if complex behaviors can arise from simple sensor-motor couplings and distributed control, even on a system with many degrees of freedom. So, to answer our question, yes, surprisingly simple, direct interactions can lead to complex, intelligent-looking behavior without complex internal thinking. The key lies in the principles of embodiment, situatedness, direct sensor-motor coupling, parallel processing, and emergent behavior from local rules. Braitenberg vehicles show us the fundamental simplicity that can generate apparent complexity, while the subsumption architecture provides a systematic way to build these robust, incrementally extendable systems, proving that intelligence isn't just about what's in the brain, but how the entire organism interacts with its world. That concludes our look at Braitenberg vehicles and the subsumption architecture. In our next episode of DeepVisus, we'll continue to explore the fascinating world of brain, mind, and intelligence, diving into even more radical approaches to agent design, including artificial evolution and artificial life. So, stay tuned.